So now if you notice it, this is the third experiment done by Mr. Faraday. So in Faraday's experiments, this is what we can say. The first one, he has been done that current is induced by magnet. Like a magnet is moved inside a solenoid. And the second one is current induced by current. Means that two solenoids will make the relative motion between the two each other, so that the current is induced by another solenoid with the help of one solenoid. Now this one is experiment number 3, current induced by changing current. This is what it is. So if you notice it, first 3 experiments, if you see, both are like you can say in a relative motion, so that the current is induced. It means the conductor is keep on changing. If you take the first experiment, it's not the Faraday's experiment. So normally I'm saying, so now if you take this experiment, so now as we know, it is keep on moving between the north and south pole of a horseshoe magnet in the up and down direction, so that the current is induced in the conductor when it is moving up and down between the north and the south pole of a horseshoe magnet. Same way, the second experiment, what we have been done, a solenoid which has been kept a non-conductor inside it, and if you make the magnet to move a relative motion, either north pole or south pole, whatever it is, going inside and coming outside. So when it is connected to the galvanometer, then it will show deflections. That is what we have been done in the second experiment. So now what is the third experiment? Third experiment, one coil, the galvanometer is connected. One coil, the galvanometer is connected, and another coil, another solenoid, it has been connected to the some current. So now when these two are, see, you can see, when these two are in relative motion, means when this coil is trying to come closer and moving away from it, then the magnetic field, because the current is passing through that, so the magnetic field created by here, as we know, the solenoid resembles to similar to whom, guys? It will resembles whom, guys? It will resembles the bar magnet. Yes or no, guys? It will resemble the bar magnet. So the magnetic fields created by it is always trying to induce the current in the second coil also. So this is what we have been studied in the last class. So because of the change in magnetic field around the first coil, will induce the current in the second coil also. Because when the change in magnetic field happen in the first coil, then the change in magnetic field also will happen in the second coil. So when it is coming forward, so always remember, pushed in, the force is more. Understanding? Pushed in, force is maximum. Which force? Magnetic force. Understanding? And if it is pulled out, then the force is minimum. Magnetic force is minimum. So in this experiment, all the cases I have already taught you in the yesterday and as well as day before yesterday. So now the thing is, if you notice it, or call your friends also. Sanjay, if you have any doubt, you can ask me. So now today's class, what we are going to do means, so he has been found that the relative motion here, if you all notice in this all experiment, either magnet is moving or conductor is moving between a solenoid or a horseshoe magnet, between a straight conductor between the horseshoe magnet. So now the last experiment which we have been studied in the last class, that is, so that now he has been found that a relative motion is not a necessary factor to induce the current produced in the change in the magnetic flux. So what he has been made means, so he has been taken a current induced by changing current. He has been proved that a relative motion is not a necessary factor to change in the magnetic flux. Also we can change by keeping, that is what is Faraday's third experiment. So relative motion is not an absolute requirement to induce the current. So he has been taken one non-conductor, that is what I have been told you, a non-conductor paper made cylinder, and he has been made a one place more number of rotations and has been connected to the current means voltage supply. So that is what it is. So now in this the current is passing. So that this coil is called as what, guys? In this is coil A. So as I told you yesterday, what is this coil A called as? Anybody? What is this coil A called as? It is called as
primary coil.
Understand, that is what. Now, and the secondary coil, it has been less number of turns, and here a galvanometer has been connected. So now if you'll notice it, this is what? It is the coil B, and this is only is to called as what? Secondary
coil.
Secondary coil. So a coil which will induce the current is called as primary coil. A coil where the current is induced is called as secondary coil. So till here, any doubt, anybody you can ask me. So now here, if you'll notice it, so we have to make on and off switch. So that I am making first now open switch. This is what my first observation. Observation is more important. Later I am going to end this lesson today with a conclusion. So now if you notice it here, guys, this is open switch or closed switch. That is the first observation. So this is an open key. Yes or no? Please respond. So what is my first observation? Anybody? What is my first observation? No current is flowing in the coil A, so that the galvanometer connected to the coil B shows no deflection. Is it yes or no? Please respond, all of you.
Sure.
So no current is passing in the coil A, so that the galvanometer shows no, the coil B where the galvanometer is connected shows no deflection. That is what the first observation. No current flows in coil A, so that no deflection in coil B. Yes or no? Please respond. No deflection in coil B galvanometer. Now, if I on the plug key, what is happening, guys? Second case, I'm going to on, understanding, plug in the key, or else plug key is kept open, closed the key. Then what is happening, guys? Please respond. So, plug key is closed, so that what is happening? So here the current will start flowing in the coil A. So when I will close this switch, then the current will start flowing. So close the switch means I will make like this. So now the switch is closed. So now if you notice it, if you want, you can draw the diagram again. The closed switch. So by the time the current is passing from like this, if you notice it, the current is passing in this direction. So at this moment, I can see some deflection in the galvanometer. So let me draw here. So this is what it is. So now the switch is closed, so that if you see the galvanometer which is connected to the coil B will start within fraction of seconds. Understand? So when I on the switch, I can see some deflections in the galvanometer towards to a momentary deflection, we can say, because the momentary current will induce in it, so that the momentary current in coil B induced, it will be deflected into some direction, momentary deflection, and within a second, fraction of seconds, again it will come back into what? When I on the switch, then the current, coil A, the current is passing in the coil A, and momentary current is induced in the coil B, and within a fraction of second, again it will come back into what, guys? Again it will come back into zero. That is what you have to remember. Only on time alone you can see the momentary deflection in the galvanometer of coil B. Again it will become back into the zero. Now even though if you on continuously. Now if it is, this is the second observation. Now what is the third observation? If continuously current is supplied, understand everybody? So continuously current is supplied, then what is happening, Ra? Current is supplied, then no deflection in the galvanometer. No deflection in galvanometer. Do you understand, everybody? Please respond. So only when during on, only I'm observing some deflection in galvanometer, and if I continuously supply the current, no deflection in the galvanometer of coil B. Next, what is the fourth observation? Anybody? Kevin? Sanjay? So now, what is that? When I off the switch, that is what it is. No spark, Nitinath. No spark will produce. When I off the switch, switch is off. Switch is off. So by the time, again I noticed it, the galvanometer of the second coil, remember all of you, the switch is off. Again the switch is closed or off. Then if you'll see, the galvanometer of the coil B will shows a momentary deflection to what? Opposite to the first case. Understand everybody? Opposite to this case. So here it is momentary deflection towards the some side. Then if you off the switch, then momentary current will be induced in the coil B, but in opposite direction. And again, within a fraction of second, what will happen? If you off the switch, again it will comes to 0. Do you understand? Only the current is induced, and within a fraction of seconds, again the deflection will come to 0. Because again the current is off continuously, then no deflection is noticed in the galvanometer. That is what you have to remember. So these are the 4 observations which have been made. Now if you notice it, when we are noticing only deflection, anybody? Nitish? Only during on time and off time. If the current is passed continuously also, no deflection. If the current is not passed continuously also, no deflection. Only during on time, suddenly it will show some deflection, and again it will come back to 0. When I off time also, suddenly it will show opposite deflection to the case 2, and again it will comes to the 0. These are the 4 observations which you have to made in this experiment. Any doubt, anybody you can ask me, please kindly. Yes or no? Clear guys? Everyone? Elamati? So now this is what observations which have been made from this experiment. These are all observations, not conclusions. Now, sir, why it is happening? That is what we are going to study. So observe very carefully. This is most important in our exam also. Now let us come to the first point. So now let us take every observation. Totally 4 observations. I will say. Sorry, 3 observations. I will say you. So now. First one. So first you can see first observation, first conclusion. So you can keep what is the conclusions of this experiment. So conclusions. So this conclusions only very, very important. So what is the first observation? You tell me guys. What is the first observation? No current is flows inside the coil A, so that no deflection in coil B. So that is what you have to remember. So now what is the first conclusion? So when no current is passing in the coil A, that is the first. I will say you observe very carefully. So now no current, switch is open. No current is passing in the coil A. This is the galvanometer. So now if the pointer is indicating only this is. So 0 only galvanometer. So now no current is passing in the coil A. So now if you notice it, if no current is passing, is there any change in the magnetic flux? Please anybody respond. Is there any change in the magnetic flux? So now here no current is passing in the coil A. No current is passing in the coil A, and this is the coil B. So if no current is passing in the coil A, no change in magnetic flux in coil A. Yes or no? Please
yes, sir.
No change in magnetic flux. Magnetic flux in coil A, because both are nil. So that what is happening? No deflection in the coil B. That is the first conclusion I can make. No change in magnetic flux in coil A when no current is passing. So that what is happening? No current is induced. No induced current in the coil B. That is the first thing I can say. So no momentary current. No momentary current in which coil, guys? In coil B. Do you understand, everyone? So that is the first conclusion. Any doubt, anybody you can ask me. Now, second conclusion. What is the second observation? Everybody read. What is the second observation? Closer the key means when the current is started passing on the coil A, then the it will see current very fastly, it will travel. So, but still we have to imagine some time. Definitely it will take some a certain time to increase the voltage or decrease the voltage. That is you have to understand. So now closed the key. So means switch is closed, then the current is induced in the coil A. So that I observed that a momentary current is induced in the coil B. So that galvanometer shows some deflection towards to the some side, momentary deflection, and immediately it will come back to the zero. That is what the second observation. Yes or no, guys? Now, why it is happening? Let us discuss. Anybody is not understand, you can ask me. Now, for example, while you are riding bike, you might be notice it. You might be riding bike. Initially, where is the speedometer indicates? Anybody tell me? Where is the speedometer indicates? 60, 80, 100. And 120. Let me take. Now, initially speedometer is at 0. Yes or no, guys? Please respond.
Yes, sir.
Yes. Others, anybody not understand? You tell me. Initially speedometer is 0. Now, when you on the bike, is it within a directly it is going? Suppose I want to 80 kilometer per hour. Is it directly going to 80 kilometer per hour, or else it is taking some time to rise from 0 to 80?
It will take some time, sir.
Yes. So now same way, I am in 80 kilometer per hour. Now I want to control the speed to 0 or else 20. Now again it is within a second it will come, or it will take some time. Definitely it will take some time. Yes or no, guys? So it will take either increasing speed or decreasing speed. So it will take some time. Yes, guys? Please respond. So take some time to increase or decrease the speed. Increase or decrease the speed. The same concept here will apply, but current it won't take even seconds. 100, like 1 by thousands of seconds, even milliseconds, microseconds, it is gains. So now when I on the switch, now the second observation, conclusions, everybody carefully observe. So as I told you, you can keep a non-conductor, so middle, so that side by side we have to keep the two coils, so the current is induced. Or else if you keep the soft iron bar, it will turns into electromagnet, and it will produces more even current. Now, if you notice it here, I on the switch. So now you tell me the momentary, the magnetic flux around the coil A, is it keep on increases or not? Please respond. The momentary, the magnetic flux around, if I on the switch, so that it will, suppose, let me, I have given 8 volt current. So in the current passing in this is, for example, I'm considering, if you take 2 ampere current is passing. So now, initially, what is the current? Initial current is 0 amperes. And to increase the current into what? 2 amperes. It will take some time. Yes or no? Please respond. Yes?
Yes, sir.
Yeah, take some time. So now during this time, when the current is increasing, example only I am taking, it is not the value. Example, initially we know that when it is open, so no current is passing. So now the maximum current will pass in the given solenoid is 2 ampere. So now if it is increasing from 0 to 2 ampere, definitely it will take some time. Understanding? So during this time, if it is 0, then what is the magnetic flux? No magnetic flux. Yes or no, guys? No magnetic flux or magnetic field. Now it is 2 amperes, maximum magnetic flux, means magnitude will be, maximum magnetic flux will be created. Yes or no? Please respond. So now if you take here, so when the current is keep on increasing, so that magnetic flux is also keep on increases in the coil A. So that is what the reason, only it will induce the current in the coil B. So what is happening exactly? See, when I will on the coil and when I will on the plug key, then current in a coil A, all of you understand, current in a coil A from 0 value to steady value. So example I'm taking, this is what the steady value, understanding. So it will take some time to increase the steady value. Yes, Padmashri, have you understand? Bhumika? So it will take certain time to increase from 0 to steady value. So during this time, the current in the coil A is keep on increases, as I told you. The current in the coil A is keep on increases to become steady value. Understand? So now, here what is happening, the magnetic field lines which are associated with the coil A, the magnetic field lines which are associated with the coil A is also keep on increases to from, when the current is increasing from 0 to steady value. So when the magnetic field lines of coil A is keep on increases, now you can see initially the coil B also magnetic field lines is what, guys? Coil B also magnetic field is 0. Yes or no? Now when the coil A magnetic field lines with the lines which are associated with the coil A is keep on increasing, then as coil B is very close, understand it is not very far, so as coil B is very close to the coil A, then the magnetic field lines associated with the coil B also keep on increases. Okay, so that is the reason. If the magnetic field is increases, then potential difference increases or not. So the coil B also magnetic field lines is keep on increases. If the magnetic field lines are increases, then because of this, what is increasing? Potential difference. Understand, potential difference is also keep on increases. If potential difference is increases, then who will increase, guys? Anybody? The potential difference is induced. The potential difference is induced in coil B. If potential difference is induced, who will induce? Please respond. If the potential difference is induced in coil B, due to this, who will change? The current is induced. This is all will happen in fraction of seconds. Current is induced because if the change in magnetic flux, if the magnetic field lines is increasing in the coil B, because it is closer to the coil A, so the whatever the field lines which are associated with the coil B, they also will keep on increases. So the magnetic field lines are keep on increases, then the potential difference is induced in coil B, so that due to this the change in magnetic field lines in coil B, so that is why the induced potential difference produces current. That current is only is to called as induced current. That is what you have to remember. So that is the reason the galvanometer will shows immediately to some side it will shows the deflection, because it is kept close to the coil A. So whatever the magnetic field lines are associated with the coil A, so they are also keep on increases in the coil B when the current is becoming from 0 to steady value. Do you understand, everyone? So that here the magnetic field is keep on increases. So here also the magnetic field is keep on increases. So when the magnetic field is keep on increases, then it will increases the potential difference in coil B also. So the increased potential difference will induce the current in the coil B. That current is only ways to called as induced current. So that is the reason it will show some deflections in any one side of momentary deflection. So now the change in magnetic field lines associated with the coil B is the cause of induced potential difference and induced electric current in it. So that is the reason the induced current in coil B makes the pointer of the galvanometer to deflect to one side. I am not saying here right or left, only one side, because based upon the direction of current, it will changes. So that is the reason it is one side, it will deflect. That is what I can say that. So who is the reason behind the deflection? Anybody? Nitinath? Nitish? Who is the reason behind the deflection in the galvanometer of second coil? Who is the reason? The magnetic field lines associated in the coil B is the cause of induced potential difference and induced electric current in it, because the magnetic field lines associated with the coil A is keep on increases when the current is increasing from 0 to steady value or constant value. So by the time the field lines which are associated with the coil B also will keep on increases. So that increasing magnetic field lines will induce the potential difference in coil B. So induced potential difference will induce the current also. That because of that induced current only, a momentary deflection will take place to one side. How many of you understand this point? Any doubt? Anybody you can ask. Clear, guys? Please respond. Yes. Bhumika, Varshini. Now the third point. So now the current becomes steady. When the current becomes steady, as I told you, third observation, you can notice it. The continuously current is supplied, then no deflection in galvanometer. All of you understand. So now here, when the current in the coil This is only very important. Exam, they will ask this only. When the current in coil A becomes steady, as we know, once it is increasing, so that magnetic field also increases. Now it will become steady. So that is there any change in magnetic field? Please respond. Anybody? Is it any change in magnetic field? So once it will become maximum current to steady value, so that the steady value, so what is happening? No change in magnetic flux. Yes or no? No change in magnetic field. So there is no change in magnetic field, then there is no change in magnetic field in coil B also. So that no change in potential difference. So no induced potential difference. Then what is happening? Then no induced current is produced in the coil B. So the pointer of the galvanometer points where, guys? The pointer of the galvanometer points at 0, or else we can say no deflection. But it is all will takes place within a fraction of second. That is why when you are on the switch, we'll see the deflection and again it will come back into the 0 pointer, because it won't take much time to become the constant steady value. So that is the reason very faster we can see the no deflection. It will come to the 0 galvanometer pointer. Understand, guys? Okay, guys, please respond. That is what. So why? When the current in the coil A becomes steady, then no change in the magnetic field. You understand, guys? No change in the magnetic field lines in coil A and as well as coil A and as well as coil B also. So no change in the magnetic field lines, then no induced potential difference. All of you should remember. No induced potential difference. Then if no induced potential difference, no current is induced. Understand, Arvind? Delivered? So that is what it is happening. Sure. So no current is induced, so that galvanometer will show no deflection, or the pointer will indicate at 0 point. So this is the third conclusion which we can make. And the last one. Now again you tell me, opposite to the second point. So now what is the last observation we have been made, guys? Switch is what? Switch off. So by the time also, then it will show some momentary deflection to the opposite direction. So in this case also the current is induced. That is what they are saying. Yes. Now you tell me. Now the third case, what is happening? Already the current is the current is passing in the coil A is in the steady value. Yes or no? So steady value, it is already there. So the current in coil A is already in steady. Understand? Current in coil A is already in steady, so that no change in magnetic field. Yes or no, guys? Yes, please respond. No change in magnetic field. So now, suddenly if I'll off the switch, now you tell me, so it will take, for example I'm saying, already the 2 ampere current is passing. That is what? A steady value. Now, if I'll off the switch, it will comes to what, guys? Like reducing speed. What will comes? It will take some time to become 0 amperes. Yes or no? Please respond. When I off the switch, yes, it will take some time, understanding? So, some time to become 0. So now during this time, magnetic field will decrease or increases. Anybody? Sanjay? The magnetic field lines. When the current is decreasing, you can see when you off the switch, then the magnetic field lines which are associated with which one? B. B means magnetic field. Magnetic field associated with the coil A is keep on decreases. So here if it is decreasing, then what is happening? Then coil B, the B magnetic field lines associated with coil B also decreases. So now if it is decreases, then again what is happening? The magnetic field lines associated with the coil A and decreases, then the coil B is also, because coil B is closed by, so that the magnetic field lines associated with the coil B is also decreases. So the change in magnetic field lines associated with the coil B is cause of induced current, because if the coil B, the magnetic field lines associated with this is decreasing, then potential difference, change in PDF will takes place. So that if the change in potential difference, then what is happening? Then the current is also will changes. So that induced, again the current is induced. Understanding? Current is induced when the magnetic field lines are decreasing. But this time galvanometer is what? This time galvanometer will show what? Opposite to the second case. All of you understand? When I close the switch, then the galvanometer deflection, if you notice it, it is opposite to the, when I off the switch, it will be deflecting some opposite direction, momentary opposite to the second case. And again, within a fraction of second, what will happen? Within a fraction of second, the pointer immediately, again the pointer, pointer comes to
Return to 0.
Comes to 0. That is what you have to remember. So only at the time of off, then the coil A magnetic field is keep on decreases, so that when it is kept closed or closed by, then the magnetic field lines associated with the coil B also keep on decreases, so that then again change in potential difference will take place, so that it is again, it will induce, it is cause of induced current in coil B. So this is what the fourth observation, conclusion which I can give from the fourth observation. So this is also, anybody's having doubt, you can ask me. So now from this I can say, so you might be noticing in this experiment, we are inducing the current by increasing or decreasing something. What is that, guys? Anybody? Let me see who will say. Humaira, Varshini. We are inducing the current by increasing, decreasing something. What is that? Anybody can tell me, please? We are increasing, decreasing, like 0 to steady value, we are increasing the current, and again we are the steady value to 0, decreasing the current. But that is not it is. So one more thing is, because of something is increasing, something is decreasing, the current is induced. What is that? Anybody?
Potential difference.
Yes, potential difference. Potential difference is happening because of whom? Before that it is, when the current is, yes? Yeah, B means what? B means magnetic field or magnetic flux. That is the reason. So if you'll notice it in our textbook also, after this experiment, you will be having one in-text question. All of you read that in-text question. What is that in-text question? What are the methods? Explain different ways to induce the current. Is it yes or no, guys, in the coil? So that is what we can say. So the process, or you understand, this is the second point. So the process by which a change in magnetic field, we are changing the magnetic field so that current is inducing. Changing magnetic field, all of you join in meeting again. Magnetic field in a conductor induces current. Induces current in another field, another conductor is only called as electromagnetic induction. Is called.
So can you say again, sir?
Electromagnetic induction. So this is the definition of electromagnetic induction. So electromagnetic induction means only the main principle is what? By changing the magnetic field. You can observe all the experiment, we are increasing or decreasing the magnetic field. When it is pushed in, magnetic field increases. When it is pulled out, magnetic field is decreases in the before experiment. Here also, when I on the switch, magnetic field is increases, so that